Hello everyone, today we continue our course and today I would like to show the searching techniques, and the basic idea for those techniques is to find the best solution or best way, like optimize it in performance. And there is basic two classical data structure searching techniques, and the first one is linear search. And how it works: when you have some array of elements, for example, given the sequence of numbers like 10, 50, 30, 70, 80, 60, 20, 94, and there is some indexes, and when you're using this approach, you need to iterate through the whole collection. And for example, if your sequence or collection is really huge, it's really hard to find if you have the big collections, because you need to iterate through the whole collection. If you have 1 million elements, it's really costs a lot of performance. And we try to implement this linear search today and to see how it's easy to implement, and you need to know only the basic like brute force technique. And here, as you see, there is some pseudo code representation. When you have some list of elements or array or any, and there is a value which you will need to find it in this collection, you need only to write a for each loop and look into the list for elements, and if that element matches, you returning the item location. Of course, if you have some object-oriented programming way, you need to find some item and return, maybe instead of index, some object. And how to implement this? We try now to implement using only the numbers, and later, after we look into different techniques, we look in object-oriented programming way to create functions, objects, and etc. And now we need to create our project. First, I write some name: searching techniques. And when we're creating the project, for example here, and while we're waiting, I write some code. And for example, you have some array, and our array is fixed size, and the fixed size is only the elements added inside here, like 50, 30, 40, 10, 20, 90, 50. Okay, we maybe create 3, 6, okay, 7 elements, 44. We create a different elements because it's easier to output then, and we need to create a function. We're creating only here, we're creating the function, int search, linear search, and here we add a array and another option, adding the searching item, or int search item. And I use the good practice. If you implementing without the headers, I recommend to implement the declaration of that in the top of main and the implementation bottom of the main. Here is better to implement because you need to say to the preprocessor to know that this method already exists, and later easier to read your code if you have the single file. I recommend it because here it's best practice to use like this to implement a function. And here you see the arrows, green and red. It's like implemented that function. And in linear search, we need to write a loop for each. If you saw before, for each item in list, because in C language we already have for each, able to write for the int item, and here we give the array. Or let's need to create a pointer. Nope. For each, maybe we need to create why it's not working. Well, begin function. Oh, it's really not that easy in the C language to iterate the array. Maybe I will create the list better because the array is a fixed size. I'm creating the list and easier to read using the for each then. And here we adding or just vector. Here is the same data structure, vector, and here adding int b. Of course, we need to write the username space std, and here we adding also on the vector, because here is dynamic structure for our int item, and here we say that he is our list. Sorry for that inconvenience, list. And here we adding the list. It's much easier to write a for each loop then, because the fixed size array it's not so easy for a moment. And instead of this array, we need to create the vector. And list. Yeah, and that means that you're able to append your list, because when you have object-oriented programming, you will always use the dynamic data structures, because the array is fixed size and you're not able to extend, or you need to use really hard around or approaches to implement your array appending or deleting items techniques. Basic here is the same as container or collection of the items. And when we have some collection items, here it's recommended not copy, to use a %. As we know before the lecture, we already know that here we give the reference of our list, and it's better not copy the whole collection twice, because when you're passing using the function, like when you're calling linear search and passing the list, you're making the copy if you're not passing as a reference, and better approach is to use as a reference. Yeah. And if your collection is not changing, you're able to write like const also. Because if you're not changing this collection inside here, you're able to passing as a constant and constant reference. And we try to do like this now and to see it's working or not. And here we need, of course, to fill our searching item parameter like 20. And here we would like to search this item. If item equals search item. And for example, we able to create our counter or count 0. And here we just counter plus plus one, another one. Okay, we just would like to know how many comparings is made it here. And we just printing this element, cout founded at index, and we write the index of our founded element. Like we need to create, we need to counter, add it here, count, and maybe instead of count we create a counter to avoid the collisions. Counter, and in the counter we also write like iterations. At the index, it's really iterations, it's really the same of counter, because you need to iterate through the whole collection, and then there is no point to write the iterations, how many iterations it takes. Because if the index is 4, you say that it takes like 5 iterations, or maybe we need to add counter plus 1. Here is a difference end line. Iterations, cout counter, and now we need to try to search. And before this you need to return some numbers, returning our counter like index, and here we returning -1. Why we need to return -1? Because if the element is not founded in this sequence, you always returning -1, that your result is not founded here. And we're creating the int sign int, and result equals, and we're searching 20. It should return 1, 2, 3, 4, 5. It's like the index 4 and iterations 5. And now we need to check if result not equal -1. We don't need maybe this. because we already printing some if you founding, and we are turning the index. Maybe we need to move from here because we creating the function, and for testing purpose we creating here the result is index. Instead of counter we creating result, and here we have the flexible function without any printings or output to the console, and later you decide where to display your output or where to use this function. Here is a usage of the function. Those 3 lines, you passing the list, we're searching the 20. Of course, you're able to write from the console also any element, and you say that found it at here, else element not founded. Element not founded. And here write end line, and we try to run it. Oh, defined reference. Why it's undefined reference now? Vector, or maybe it's const, or maybe we don't need to use the list because the list is here. When I talk about the bad practice, when you're using namespace std, and if you're using the list, for example, the list also is inside the std library, and when using the same name, like it means like vector and list, and here it's like basic std list. When you write the list, it means like this, and here is a collision. Here is not variable, it's takes as a std list. You need better to delete this, and here to use std always like this, or instead this use auto keyword, also able to do like this. And here, as you see, it's really easier to make this collision, and if you're not using the std, using namespace std, you will get a lot of those type problems. And now we try to see, is it working now? Nope. Linear search and defined reference. It's not, maybe it's wrong. Why is undefined reference here? Maybe here is a const std vector list. Oh, here, wrong one. And as you see here, only the single symbol able to make those type of problems. And define reference because we changing here, but not changing in declaration. The %, and here is makes some problems. Now it should work, and as you see here, found it at index 4, iterations 5. And of course, you're able to print it out your element. Like if you would like, you're able to print it out, cout, and your elements, like the list and results, like this, std and line. When you have the vector, it's really easier to get the element. You're able to use function at, or to use this brackets, and to enter the index, and you get the element of this index when using the vector. And here it's founded element. Founded element, founded value, maybe. Founded value. We run again. And founded at index 4, iterations 5, founded value 20, as you see. And if you would like to search some items, you're able to read from console, cin, different way, like input, and here int input equals 0. Here you would like to print it out, cout our text, like enter search item value, int value, and here maybe we adding without end line, and we have the input. We're reading the input and passing this input here. Now we try to enter search value like that. And as you see, found it at index 3 and iterations 4. Founded value 10. We're trying again. 44. Found it at 6, 7, and 44. And if you're adding not exist value, like 25, element not found. And that's it. Here is a brute force approach for your searching. And if you have 1 million elements, you need to iterate 1 million iterations have here. And for huge collections, it's really not the best approach. But if you have really small collections, it's really not a bad idea to use like this. But always you need to think which type of algorithm you're using and how fast your collection grows in near future. And the linear search is finished here, and now we're moving to the different approach, how to avoid that many iterations. But of course you need to have the different aim when you're using the binary search. The binary search technique is also it's really classic way how to get better result, but you need to know that binary search, the sequence which you will use, you need to be the sorted sequence. You're not able to make not sorted sequences. You're not able to search in not sorted sequence or not sorted like trees, because binary search also using in a tree data structure. and it's really a good technique. And the biggest feature or difference when using the binary search, we basically ignore half of elements just after first comparison. Like we need to have any size of collection, and we dividing by half after the first comparison. We comparing the X element or searching item with the middle element. And after this, we moving to the left or to the right side of collection, and we ignore the left or right side. If the X or search keyword matches with the middle element, we returning the result. For example, we able to get in the best case using the complexity big O notation or in time performance complexity, we're able to get constant time if you get if the middle element matches the search key. Else, if X is greater, we lie the ref and etc. Like the basic idea is to have the subarrays, like the right subarray and left subarray. And if you moving to the deeper, you dividing those arrays by 2 that many times how many you need it. And better is to look into our visual representation. If you have the, of course, ordered or sorted sequence, first you have like from the 0 to 9, 10 elements added here. You dividing into the half, and you find your middle element. For example, 16 is the middle of element. We're searching 23. And 23, is it more or less than the 16? If the 23 is more than 16, then we move to the left of half. And of course, we repeating the steps that many times, how many we need to repeating those steps. 23 is more because our 16 is middle element and 23 is more. Then we take the right side of our of subarray and ignore the left subarray, and we have only those 5 elements left here. And after this, we moving more into deeper. We find again the middle of this left subarray, like black color, it's not used already, it's removed. Like it's really not deleting from the memory, but you're not looking on those elements anymore. And here we have subarray, we found a middle element, and 56 is more or less than 23. If 56 is more, then you take the left subarray and remove those three values, and you look into the left side and you try to find the middle of element. And if middle element is 23 and you comparing with this, you found it your element. When I implementing the function, maybe it's more easier to understand then. Then look into this schema. The basic approach, basic idea is to divide by the half and to remove some left or right portion of the elements from the array or any list or collection. And how to implement this binary search. And basically we're creating another function, and we're using also integer returning binary search, and we passing the also maybe vector int, and for binary search you need to passing left, right, and searching keyword. Int left, I know maybe I write the keyword left, int right, and int search key. Okay, we look here. If you have any questions, of course, able to ask it here. Will be in the description of this video. Okay. Later I will share this code in the video and also in the Moodle course. Of course, I leave these examples. And right, it's okay. Right. Richt. Sorry, spelling. We have the binary search, std vector. We have the left, right. Basically, why we need this left and right? We have the sequence like this, and we need to get the range. Like to get range of the first element always will be the 0 at the start, and later we'll change this index. And the last one is the last element, like 1, 2, 3, 4, 5, 6, 7, and from 0 to 6. Here it's left and right. Oh, sorry. Left and right. Left is 0, 6 is right. First, we need to know that range of our collection. And the list, which is where we're searching, and search key, it's what we will need to find it. Like search key, any value we need to find it. Okay, we need to implement binary search. Now we're moving for implementation. And here also, oh sorry, we need to add the list. And here we write also in binary search and list. Okay, we need to implement here. And the first, we need to find the middle element. Compare X with middle element, of course. First, we need to find the middle element, that element here. Or to find the element inside this list. I just take it here. We need to find the middle of element here, or in any sequence. And how to find this middle element? You need to only use the simple temporary value or middle element. Middle equals, and you need to write a formula of this middle element, find the middle element. And the formula, it's really not so hard. You need to have this approach, like you have the left, you have the basic, the first element, for example, and you plus your right. How to get range? You get the right, left and right, it's range of your elements, like left here 0 and 6 is the last element. And of course, when you have the programming, you will get 7 elements here. And if you get the size of the list, it's 7. It's not correct because you need to get the 6. And to get the 6, you need to write size minus 1. Because here you're passing your collection size. For that reason, you need to remove 1. And here you need to have the left, the first element. And after this, we need to divide our array by 2. Because we need to find the middle of element. And when we have like 3, 4, 7 elements, you make it like this. First is 0 left, plus 7 minus 1, and divide by 2. If you get the different, like 6 minus 1, it's 5, divide by 2, you will get 2. If you have the 7 minus 1, you will get to 3. That means you will get the index of the middle of the middle element, like this one, 0, 1, 2, and 3. Okay. Here is the index of the middle element. Index of middle element 3. Okay, now we need to read our sequence or list. While the left is less or equals right like this. And of course the left, as you see here, is 0. Less equals right at the moment is 6. Yeah, it's maybe 6 here. And of course you're executing the next step. And the basic algorithm is, as we see here, compare x with the middle element. And compare the x for now it's search key. If our middle element, and how to get from the list middle element, we need to call the list middle equals search key. And if the 3 in the list 3 here or middle equals search key, we passing, doesn't matter which key, it's any or like 20, 30, 10 or any element, we comparing. If is it matching here, you're returning the list. Oh, sorry, not list or middle. because we need to return the index. Returning founded element index. Or return founded element index. If you matching here, you will get the result instantly, like constant time. And you also need to write else if or if to compare the different ways. Like if we return mid element, else if greater than the mid element, then write half. Smaller, we left half. Okay, if our list middle less than search key, else more, yes. And if the middle is less, we make that less equals middle or left middle plus 1. Or maybe it's greater, I'm not sure, wait, I need to check. If x greater than the mid element, then x can only lie in the right half. Okay, for our reason, if we looking for search key looking, for example, 20. Oh, sorry. Here is a problem because we have not sorted sequence. If you have not sorted sequence, you're not able to do the binary search. I forget to say for you this, and if you have that way, it's not able to use the binary search. First, you need to sort elements, and for our testing here, we're not using the sort algorithm at the moment, but you're able to use the sort algorithm we use later during the examples using object-oriented programming. And now we need to use the different list. We copy here, sorted list, and we creating like 10, 20, 30, 50, 7. We have the same 7 elements. We have sorted array or sorted list, and we adding here sorted list, and we searching for maybe more. We need to find the 7. And our middle element is 50. If the middle element is less than search key, we moving to the right. We moving to the right sub-array or sub-list. After the first iteration, here as you see, our 50 is a middle element and we searching 77. 50 is less than 77. True? Yes, is it true? And if it true, we moving, or I don't know, take the right right sub list, because we need to change the left. Why we need to change this left? Because when we changing the left from the 0, because the first range we're starting from 0. If you need to move and take the half elements, you need to move your pointer or index on the right half, on the right side. If you need to take the right subtree, and you will get your right side. And 0 plus middle element is our 1, 2, 4. It's 3. 3 plus 1. And you will get 4. That means you will go to the first, second, third, 4. 0, 1, 2, 3, and 4. You're moving here to the fourth here, to this sequence. And later, if the middle element is more than this key, you move to the left. Sorry, I need to open our search techniques. Forget which side we move. R, yeah, left and right. Okay. We move to the right, equals middle minus 1. Because we move to the right sublist, and if we moving to the left side, we moving from the right to the left. And here we taking left sub list, and as you see, right equals, at the moment we have right 6 minus 3 minus 1. Is it equals 2? You're just reducing, or if you're moving to the right side, you adding the one you increasing the index of the middle element. If you're moving to the left sublist, you decreasing your middle element by 1. And as you see here, 4 and 2. Here it's universal approach, because you need to divide your list. Like if you get this one, next will be the 99, and if the less, move to the here. And when you get this last value, you just searching if it equals to the search key, you're returning the result instantly. And here you need to return minus 1 if you're not finding anything here. And of course, here it's a basic implementation. It's really not so hard. And basic libraries like STL in C++ also have this approach already implemented. You need to use only the function. Here it's implemented by ourselves, this binary search. And now we try to test it is working or not. And we need to check it here. The binary search. We need to pass sorted list, because without sorted list it's not working. We need to pass 0, because the first iteration, the left will be always 0. The right will be the size of the sorted list. Sorted list size -1. Right, yes. And search keyword, for example, 77. And now we need to get index. Or just founded value. Maybe we need to use like this separator. Founded value and search key, and now we need to print it out. Our result. cdc out, founded value is index, and if founded value not equals -1, we returning this, else element not founded. Just copy this and maybe I copy from here, it's easier to write. Founded value and here sorted list, and here we getting the index founded value. And when we looking like this, we should get the result of search key 77, the index here. And we also maybe need to print it this. Oh, sorry. Sorted list. Founded index. Founded value. Founded value. Oh, here it's maybe need to change. And we adding here, and here we need to leave that on the founded value. Here is index, here is value. And now we try to run it and see the results. Oh, sorry. Here is before that, element not founded. It's not working. Okay, I need to comment it here. That one. And try to run it. Okay, we get the loop. Is it infinity loop or not? I'm not sure. Okay, we have the list, we have left, right. Searching techniques, I will look left, right, left plus, right -1. Left, right, left. Okay, we try to pass then 6. Okay, and here it's okay, left 0, sorted list. Binary search. I've tried. Search key. If maybe we need to return in here. No, here. List middle. List middle equals for search key +1 else right middle -1. Why is not working? Maybe we need to try to comment this to see the same. Sorted list. I'm not sure what's happening here. Maybe we try to change a bit. Instead of this, use the list at middle. This is corrected here while else if list equals search key. Everything is fine. I don't know what's happening here. Maybe we try to implement using the simple array. Simple array then. Middle +1 middle. Search key. What's happening here? Try to add a breakpoint here. Oh, we don't need this. 10, 20, 30. Sorted. Okay, we need to pass here. commenting this out. std cout found. Okay. Try to I'm not sure what's happening here. Maybe I make some mistake and I don't know why it's not working now. Binary search. Left, left, right. Okay, maybe I create a basic array, and when I found a solution, what I made some mistakes, I will let you know. And maybe we use simple array then, and array equals, int array equals the same list. And instead of here std vector, we use the int array. With binary search int array, and after this we changing here array, and here we changing array middle, array middle. Pointer to the const. Okay, we don't need a pointer to the const at the moment. We need pass array. And when we passing the array, we should get the output. Binary search. No matching function called binary search. Here. Okay, now it's okay. We changing the sorted list to the array, or sorted array. And now we try look our size of array, and size of array equals array, size of array divided by size of array first index, first element. And here we passing the size of array. And here we calling array founded value. The index is. Okay, now we try to output our result. We get the same. What's wrong then with the code? left less than equals than the right. We're not updating the value, maybe. Or we're not. Yeah, you must add it inside the loop. Okay, the first problem here. And maybe we'll find more problems. Okay, I need to back our implementation and we're using the vector. And here, of course, we need to move down inside the loop because we need to update this value. And here also, as you saw, sorted list founded value. Okay, try to run it again. Element not founded. Now start working, but not correctly at the moment. And sorted list size 77. Okay, we try to add it maybe 30. Oh, 30 is working. Okay, then we have some issues with different implementation. 30 is founded at the index. Okay, we look here. Uh, 30 is index 2, as you see here. And if we take the search key 88, element not founded, 99, and if we try 50, maybe it's working. Yeah, 50 is working. Found it. And what's problem here? We have some problem with updating of the right, maybe. If list middle search key, we moving to the right sublist. Okay, looking into L equals +1 or equals M minus 1. And here is working. I think that here is working. Okay. Why not working here? I'm not sure now. 3 and 50. Sorted list size. Maybe there is too much this return. If while left, right. I am not sure it's okay implementation, but it's not working. Maybe I just copied this implementation, try to run it and check it. Is it working or not? Copy. Searching techniques, adding here. Binary S, and we just using here instead of this binary S, we pass in the array or here it's not the array, sorry. Then we are running here binary S. And here we try to run binary S and to see that it's working or not. Element is present at index 3. Okay, we adding the 3. Element at index 1. I don't know what is the difference between that one and that one. Array M. Okay, we try to implement using the object-oriented programming and to use the same technique to see that the result is the same or not. Searching, sorting. I leave this code here also, the basic implementation, and we try to create some objects and to see that it's working or not using the array, or instead of array we creating the different method. And we creating, for example, the person object. And when you're creating the person class, we creating and ID and age, std string name, include istream, and we creating a constructor, all fields to create object. Alt insert, we create getters to accessors to get some age, ID and name. And now we try to implement binary search and to implement the sorting also using this. We're creating int binary search by person ID, and we passing ID. Binary search by person ID. Generating the function, we need to implement binary search by person ID. And we need a collection. For example, we're creating the collection inside this function for easy purpose, but to use able to use the different outside. we're creating the list, or we just creating a header file. It's really not a big deal. And here we're creating the list of person object references. Persons, sorry, std, and we need maybe create vector instead, easier to use it. Include vector. We have the string name person, and we need to also create a function which is comparing elements. Bool compare person by age, and we need to pass person 1, person 2, and we need to create as a static because we use as a comparator here, comparator for our function later. Return p1 get id less than person. We need for the sorting this function get id. Here is comparator function in Java, or if using lambda expressions in C++, also able to different approach. At first we need to sort our collection. We have the persons, yes, here. And first we need to add some persons, push back, and added new person objects. If you need to either approach, you're able to use auto keyword. Auto Peter equals new person, and create like ID age 2, name Peter. We create some objects. Peter, John, and Catherine. John, Catherine. 22, 33. We just adding Peter. Persons push back John, and persons push back Catherine. Okay, we have the filled our list of persons. We need to sort. Std sort sort our persons, and we also need to add it the library algorithm, because sort function is from algorithm library. And here we're adding the comparator, comparing by age, using a static able to use like this. Oh, sorry. Need to use no matching call sorts. Person sort function. P.to get person begin, person end. Oh, sorry, forget. Here is a vector, and for vector you need to, of course, show the person range begin and persons end. Like you need the range of your list of vector, the collection begin and end, like this, from 0 to hero, like this, from 0 to the 3, to the range of this, and compare by age this collection. Sort function, we have sorted function, and now we need to implement our binary searching, and we need to have the left and L left equals 0 and right equals person's size. Left, right, and such key will be ID. And while L less than equals R, we implementing and middle equals R plus R minus 1 divide by 2, and if our person's vector middle less than or equals ID, we are returning M or ID 3. And here we need, of course, get our ID. If persons M does get ID less than ID, we should change our middle plus 1. Else right equals M minus 1. And the final result is return -1. Okay, here is a function which is sorting our person list. We creating the person comparator, and after this we implementing the binary search function inside here. And now we try to binary search some person using the ID. It's really the same as we saw before, and we try to see is it working or it's not working also. Okay, we try to, instead of binary search, to call our person, import person age, need to add it person age here, and here we calling our person class, or we need to create person p equals new. Oh, sorry, we have already implemented person binary search. Doesn't matter, we're able to create any person like we would like. Binary search, and we're adding the ID. For example, we need to find the person ID like John or Catherine, and when we adding the Catherine here, we should find something. found it value and not sorted list here. We don't need this. We need founded at index, and that's it, or not founded. The same stuff. Or not same stuff. Oh, maybe it's founded index 0. Okay, now we try to look into our different element not founded. Yeah, here are some problems. I don't know what's wrong here. I have working example here. Here, like when you're searching, I adding maybe this example later after this, because I'm not sure what's happening here wrong. Because here it's implementation, I have the basic binary search like this, and also here we're able to find the sorting, working sorting, and searching by keyword, by get ID, for example. And when you're searching some person, it automatically generates HTML file and showing your that find it person, like ID, like this. And here you're able to pass any ID, like Catherine, get ID, for example. When you're running this, you're running the concrete person and you will get the result. And here is implemented binary search. Here, I don't know if there is any difference here, because I don't see any difference here. I'm not sure why it's not working. Maybe it's not working for that reason, because I need to -1 first to know the real size, and to -1 here also. Yeah, maybe here is my biggest problem today. Let's see if we try to remove person size, -1, and see is it working here. Element not founded. Not founded. No, maybe some different problems. I don't know what's happening here now. Okay, sorry for that. And I will put the correct one implementation in the Moodle and in the video down below. But the basic idea is to divide these elements in the separate parts. And here there is implementation of the same function. I really don't see any difference at the moment, because when the middle less than search key, it's left +1 and right -1. If you find some problems, please let me know, because at the moment I don't know what's happening. And here you'll find the basic implementation of linear search and binary search. Of course, the linear search is not useful when using the searching. Better to use the binary search. And here you find your implementation. Maybe next week I try to find this problem and see why it's not working. And later we're moving to the hash table, and to see what is the map data structure and how to use it. And maybe we start using the already implemented code, because as you see here, we get some problems. Of course, when we're getting the problems, it's easier to learn because you need to solve this problem. And when you try to implement, of course, better try to implement yourself, because as you see, I don't know, I prepared this yesterday and it's working like a charm, but while implementing again, as you see, it's not working, and I don't know why it's not working now. And we need to fix this problem, and later I maybe check this code and see what's problem was that. And thank you for your attention. Please ask any questions using the email or in Moodle. Try to ask, and of course we're using the team tool also, able to make the audio conference for that purpose. And if you have any questions, we're able to use the voice communications, and I will help you, or if you have any more questions, you just write some email. And thank you for your attention. And for today, that's it. I added those links to the example, to the code, and I added to the working code first, and later when I fix it, I just say why it's not working and which problems you will get when you're implementing this and why it's not working. If you're writing the correct code but it's not working, maybe it's not correct code. Okay, thank you for attention and see you next week.